So when I think about big data, and I know I listened to your first podcast and you talked about, that everybody wants to go find the newest, latest, greatest tool. And sometimes we get fascinated with the shiny toy, and that I think can be a problem. One of the powers of big data is we not only have more rows of data, and I don't know that we need more rows of data to be smarter. Oftentimes, like when I hear people analyzing data sets with, millions and millions of rows, I'm not convinced you couldn't randomly sample that and come up with the same answer with a much smaller data set. But what I find powerful is the columns, the amount of information you get, and how the tools now can help you sift through hundreds or even thousands of possible features to find the ones that actually have predictive power.
Welcome to the Conversations on Applied AI podcast, where Justin Grammons and the team at Emerging Technologies North talk with experts in the fields of artificial intelligence and deep learning. In each episode, we cut through the hype and dive into how these technologies are being applied to real-world problems today. We hope that you find this episode educational and applicable to your industry, and connect with us to learn more about our organization at appliedai.mn. Enjoy.
Welcome, everyone, to the Conversations on Applied AI podcast. Today on the program, we have Kevin Church. Kevin is a data scientist and Six Sigma Master Black Belt, a chemical engineer by training and applied statistician by vocation. He has more than 20 years of experience in the practical application of statistical thinking and the scientific approach to improve business performance. Kevin helps organizations by leading teams on predictive analytics, executive coaching, and everything in between. He spent the past 3 years at United Healthgroup and has been involved in co-founding and building multiple meetup groups that focus on educating attendees on data science through competitions and helping nonprofits. Welcome, Kevin.
Thank you for that introduction.
Yes. Well, maybe as a starting point, you can maybe give listeners maybe a short background on yourself and the trajectory of your career that sort of got you here today.
Well, as you said, I'm a chemical engineer, and I started out in the oil industry, grew up in Minnesota and moved to California after graduation. And after about 10 years in the oil business, I met Dr. W. Edwards Deming, who some of the listeners may remember was the American who went to Japan in 1950 at the request of the Japanese government to help them improve business processes. And improve he did. And so when I was a kid growing up, made in Japan had a connotation of being kind of cheap, but junk. Things like Japanese toys wouldn't last very long. And now today you have like the most reliable automobiles in the world are produced, for instance, by Toyota Motor Company. And that's a direct result of the influence that Deming had. So by the time I met him in 1987, he was 87 years old, still going strong and teaching these 4-day seminars that would have thousands and thousands of people in them. He said at the start of that seminar that I was sent to, and I frankly, I'd never heard of him.
Yeah.
So I fly off from California to Chicago, and I'm in this room with 2,000 other people. And he says, if you pay attention to what I'm about to teach you, it can change your life. And I may have been born in Minnesota, but I'm kind of from Missouri when it comes to stuff like that. And so I'm like, yeah, that's not going to happen. But I'll be darned by the end of the week if I wasn't getting in line to get my book signed. And it really did change my career trajectory.
Really?
In that I learned the value and the importance of delighting customers. And you do that by improving your business processes, and that the customer is really the focus of all that you do, and the act of, increasing shareholder value, turning a profit, all those things are consequences of taking really good care of your customers. So that was a valuable lesson.
Nice.
Along with, I had a chance to work with one of Deming's masters, a gentleman named Dr. Harold Haller. And Harold is, in my opinion, the finest applied statistician in the world. And he had come out of Goodrich Chemical Company, and he was running a consultancy when we met him. And I learned from him this transformation, this process you use to convert data into information, into knowledge, and eventually profound knowledge. And that progression, which a lot of times I see even people today with all the power we have at our fingertips and our computers, we stop at taking the data, extracting the data and putting it in an Excel spreadsheet. And that's what we talk about, tables. We don't even bother to graph it. And this isn't graphing in the sense of a graph database. This is just create a picture.
Yeah, sure.
Put the data into a picture, and a picture is indeed worth 1,000 words. And then you can learn something. And so that's the knowledge part. But what Deming talked about was you needed to go one step further, and that was profound knowledge. And he really thought that was what the role of the leadership in an organization should be, to understand the causal systems to such a profound extent that you can actually predict performance,
Right.
which is a lot of what artificial intelligence is driving for, is predictive analytics. And Deming was talking about that, because if you can understand the causal system to a profound extent, then you can understand those parts you have control over, those parts that you have to be able to react to, that you do not have control over, and the parts you can control, then you can tweak to try to improve your performance. And again, in Deming's world, it was all about delighting the customer.
Excellent. Excellent. So you were doing this in a chemical engineering sense at this time, correct?
Well, it started in an oil refinery, but the concepts that Deming taught were pretty universal.
Sure.
So it really can be applied anywhere. So after a couple of years of being a client of Dr. Haller, then I transitioned into being one of his employees. And so I was a consultant with his small firm for 10 years. And then I've also freelanced since then for about another 15 years.
Okay.
And so I've worked in healthcare, manufacturing, oil, chemicals, nuclear power, water treatment, medical devices, and even one time I helped a radio station analyze some of their
Mm.
customer response data. The tools
Mm-hmm.
are pretty universal, and every going enterprise has customers. And so if you've got customers and you've got data, then there's hope for you, because we have the tools and the methods to be able to improve things.
Yeah. I guess maybe walk me through this process a little bit of data, information, knowledge, and profound knowledge, and maybe how does Six Sigma sort of apply to that? Because I know a little bit about Six Sigma, but maybe you can enlighten our listeners sort of how that works and how that plays into this.
Well, and I'll use an example from current events, if I might, and that is with the tragedy of the killing of George Floyd in Minneapolis on Memorial Day. And anytime there's a tragedy like this, particularly the ones that revolve around gun violence, there will be lots of people who want to jump up, raise their hand, and propose a solution.
Mm.
And we call that jumping to solution. And what happens is, if you jump immediately to solution and you don't, do the work of getting to root cause, which is part of what, when you're converting data into information, at least in the world of Six Sigma, often what you're trying to do is understand the causal system so that you can figure out what you can tweak or change or remedy to improve the outcomes. But if you just focus on the solution, it's like getting shot by a gun and putting a band-aid on it. That's not going to help you. May seem like a good idea, but it's not going to help you. The quick fix, the jumping to solutions, is expedient. Politicians, I think, want to be seen as being proactive and kind of taking charge of the situation. But inevitably, because there's, for instance, the war on drugs. We've been fighting that war for as long as I can remember. I mean, remember Elvis Presley went to President Nixon and wanted to be the drug czar.
Yeah.
We're still fighting that war because we haven't really addressed the root causes. And so that's kind of how that transformation and the data plays into that, is if you want to understand the causal system, you've got to get into the data. That's the best way to do that.
For sure. And as you improve the process, is there like a looping cycle that happens, I guess, with regards to, we don't have enough data right now, we need to go out and get more, and once you get more, can it feed in where the whole direction goes?
Well, sometimes there's kind of two situations, and this is where we'll talk about the lessons from the data science Venn diagram, which anyone who listens to this podcast can just Google data science Venn diagram and images, and you'll get all kinds of examples. My favorite one shows these three circles, and at the intersection, there's a unicorn. And a little side note is, if you are in the job market for a job in data science, you will often see the job descriptions are written as if they're in search of a unicorn.
Right.
And frankly, I don't know what the solution to that problem is, but the reason they put unicorn as at the center of that is because they're rare. And in my work, I think I've only met one or two unicorns in my life. And that's people who have outstanding, hacking skills, coding skills. They are also the subject matter experts. And then in the diagram you'll see online, they'll put statistics or math and statistics in the third circle. And I really think that's too narrowly focused. That should be process improvement, which could include the math and the statistics. But all, like data science applications, in my opinion, are ultimately efforts to improve something, improve some process, improve an outcome, improve a result. And therefore, we ought to be kind of systematic about how we go about doing that. In process improvement methodology, particularly in the world of Six Sigma, there's the DMAIC, this 5-step methodology where you define a problem. In the measure step, you create a baseline to prove in data that in fact the problem exists. And then you do work. The third step in analyze is to get to the root cause. And then the fourth step, you finally get to solutions. And so rather than jumping straight to solution, there's all this due diligence you have to do up front to make sure that you arrive at the elegant solution. And even that you'll test on a small scale. And the elegant solution is solve the problem, don't create any new ones. So when I first heard this concept of defunding the police, and maybe I'm getting too political here
No,
for an AI podcast, but I thought, well, that'll never work because they're just human nature. It's like saying we don't need regulation of business. Look how that worked for us in 2008, 2009. So no, you're going to need a policing function. But now, if you look, there's more nuance to it that I'm learning now, in that they want to kind of redirect some of the funding.
Yeah.
And I heard the city of Minneapolis has actually got some research going on where they're analyzing 911 calls to look at what the nature of those calls are, because they triage the calls into 3 departments. Is it fire? See, it was fire, police, and maybe ambulance
yeah,
for the 3.
Yep.
And they're saying that a lot of the ones that it's like fire and ambulance and everything else goes to police, but some of the police ones, like the domestics, maybe we don't need to be sending people out, who are as highly trained and armed as the police officers are.
Sure. Maybe somebody that can just calm the situation by coming in and at least appearing to be police rather than instead maybe a social worker or something, right? So
that makes sense that you'd look at the data, you try to understand, and you always have to ask yourself the question, what problem are we trying to solve here?
Yeah.
And the elegant solution, again, is one that doesn't have side effects. If you simply defunded the Minneapolis Police Department, there would be all kinds of adverse side effects from that.
Right.
And that's typical of jumping to solution. As you give the appearance of doing something, you may make the particular problem you're addressing go away, but in likelihood, you will create new problems that may actually be worse. And so that's why we want to get to root cause and then test solutions on a small scale to prove that they are elegant, solve the problem, don't create any new ones.
Yeah.
And then in the last step in the Deming process, you can ramp that up to full implementation as makes sense, so that when you've tested it on a small scale, if it doesn't work, then you're going to learn a lesson and you're keeping the tuition costs low by initially testing on a small scale.
Excellent. Very cool. Well, you had a little formula. It was E equals Q times A. Is that right?
Yeah, that's one I learned it'd be 3 years ago next week that I started working with United Healthgroup, initially as a Six Sigma trainer. And my boss, Bev Harbrecht, had this change formula that E equals Q times A. Now, this isn't algebra. This is more conceptual, but the E is the effectiveness of some proposed solution. And that solution might be some AI application that you've built out for a customer. And then E equals Q. The Q is the quality. So it's basically how good technically is that solution, like on a 0 to 10 scale. And then the A is the acceptance. So it's Q times A. And the A is how well accepted is that tool by the user community. And one of the first times I taught this, one of the students in our class came back to me the next day and said, well, I built this really cool application that reduces, I'm trying to remember, but it was over 50% of the effort or hours required to do this particular task. He automated and cut the time by more than half. He said, but I never went back to see how many of my team was actually using it. And he found out that only 40% of the team was using the tool. And so if your solution's a 10, your quality's a 10, but your acceptance is only a 4, then you've stopped short of what you could have achieved. And the acceptance side is really the people side of the equation. And we could spend an entire day talking about how you do change management, but for sure the people that are going to be the recipients or the users of whatever cool tool you build, they need to be involved initially so that you understand the problem they're trying to solve and you engage them throughout the process so that they have their inputs in there and they have some ownership, and that'll likely improve your odds of the tool actually getting used.
Yeah, absolutely. I mean, I think about products and projects that I've built for companies, and they haven't really interview the customer, right? You talk about voice of the customer, I am assuming in this whole process. And if it's painful to use, your customer, even though you're right, how cool it is, if it's painful to use, they're not going to use it. And so you really need to make sure you get acceptance from whether it be the end customer or even the internal team, it sounds like, right? Yeah, for sure. For sure. And so just with regards to building cool things, have you seen teams just building models for the sake of building models, again, not fully understanding what they're going after? And what are some, I guess, some pitfalls you've seen and some ways you've tried to maybe address that?
Well, I should know better, frankly, but I'm as guilty as the next person. And if you put a good data set in front of me, I'll want to dive into it. And my favorite example of this was, Justin, you might have actually been involved with this, but there's a housing nonprofit in Minneapolis called Aon that was
Hmm.
having difficulty with what they called their water appliances, which are basically things like toilets and faucets, and leaking in the buildings. And their tenants, who all were low income, aren't charged a water bill. Like, for instance, if you own your own home, you've got a water meter in your house, and that's how they decide what to bill you. And the onus is on you to make sure you maintain your water appliances so that you're not wasting water because you'll get charged for it. But in these buildings, Aon was eating it, and so they asked us if we could build a model that would allow them to monitor the billing information and identify rental buildings that had likely problems with appliances.
Right.
And so we did a great bit of work in a Saturday meetup, and we had prepared the data in advance. And we had two teams. I led one team that was taking more of the dinosaur approach, so just a linear regression
Yeah.
model. And we had our model, at least a rough model, done by lunchtime. The other side of the room, we're using Python and coding, and we got done one model for one building before they did. But a couple hours into the afternoon, they'd built models for like all 50 buildings,
Right.
because once they wrote the code, they could just run the data. And so we then built a tool that when they uploaded their billing information for all these buildings every month, they could identify the buildings that were suspects.
Yeah.
So it was a pretty cool application of data science. However, I was doing some work with the city of Minneapolis not too much later and learned that the next generation of water meters for buildings and residences can be read via Wi-Fi.
Mm.
And so the city is, right as we speak, they're in the process of changing out all 89, I think it's 89,000 water meters,
Mm.
and that's residential water meters in the city, or at least it's bigger than the city. It's their service territory. And they're going to be able to read them all by Wi-Fi, potentially in real time. That's not their plan,
Right.
right? They just have to read them for billing, but you could read them in real time. And I thought, well, if you've got the technology where you can read the water meter in real time, then you could simply put those meters into these rental buildings,
Yeah.
and you could establish a baseline, like in the middle of the night when most people are sleeping,
Yeah.
what is your water consumption?
Right.
And you could put that, and this is where kind of I go back to the Six Sigma and the need for statistics is there's a tool called a control chart. Basically, it's a way to look at data to see if a process is stable, random variation about some central tendency. So there's probably some small amount of water use, background water use in a building of that size that you could measure.
Right.
But if you get to where you have, and it turns out it only takes one toilet with a leaky flapper valve, and the water consumption goes up enough that you can pick it off the meter head, and a control chart would set off an alarm, and then you wouldn't have to wait for the bill to come out,
Mm-hmm.
right? You could send someone out the next day. And with the technology, you could probably have a system that monitors that control chart, spits out an email, and sends it to the building maintenance manager, and the next day they could be investigating.
Fascinating. Yeah. So because of the new technology, it kind of flipped the whole solution
Yeah,
on its head that the
right.
teams had originally come up with.
Well, and it's the risk of being a data science meetup is we look for places to build models, and that's one that maybe a simpler solution might have been more elegant.
Yeah, yeah. As I think you said, if you own a hammer, I guess everything starts to look like a nail. So around model development, right? Do you have some common practices that you typically follow? Some pitfalls, things that should be avoided?
Yeah, I do actually. And again, this goes back to the first model I ever built was probably in 1989. So I've been doing this for a long time, mostly linear models, often like in the oil industry. And even when I worked at the New York Times and other newspapers, we were using linear models most of the time with a continuous dependent variable, but also some logistic regressions when we had a binary dependent variable.
What were the tool sets at that time?
Oh my gosh.
Just curious.
I mentioned Dr. Haller, this applied statistician, and he had a programmer write in Fortran.
Oh,
He had a
wow.
tool for designing experiments. He had one for doing multiple variable regression. So what we call linear regression, but you're not limited to linear. Obviously, you could introduce terms to build curvature into your models. And then they had another Fortran program that did multiple property optimization. So that was all. It was all proprietary
Custom.
and right and built stuff. And then when this next generation came out, he had programmers in India who were writing things, I think, in C. But after I left the New York Times in 2002, I started using Minitab,
Okay.
which is a tool I think that came out of the University of Pennsylvania. And actually, one of the founders of that was another Deming master, a guy named Brian Joyner, Dr. Joyner. And so I've been using Minitab. That's what the Six Sigma people at United Healthgroup use is Minitab. And so that's my tool of choice. And although I'm fascinated with the programming languages and I can now get around in SQL and do a little bit of work in SAS, Minitab is so much quicker because of the user interface. But again, not as powerful.
Sure.
If you have to build one model, I'll get done before you do. But if we're going to, like you remember our first meetup group we did here in town was predicting sales at fast food restaurants.
Right.
And we had 50 restaurants. So I ended up building 50 models where the people who were coding built one
Yeah.
and then just replicated it. So I don't want to be disparaging about it may sound like I will in a minute here, but I don't want to be disparaging about how beautiful the technology is. And just, let me comment on that for a second. So when I think about big data, and I know I listened to your first podcast and you talked about that everybody wants to go find the newest, latest, greatest tool.
Mm.
And sometimes we get fascinated with the shiny toy, and that I think can be a problem.
Yeah.
One of the powers of big data is we not only have more rows of data, and I don't know that we need more rows of data to be smarter. Oftentimes, like when I hear people analyzing data sets with millions and millions of rows, I'm not convinced you couldn't randomly sample that and come up with the same answer with a much smaller data set.
Mm.
But what I find powerful is the columns, the amount of information you get, and how the tools now can help you sift through hundreds or even thousands of possible features to find the ones that actually have predictive power.
Mm-hmm.
And that's where the power, I think, of data science to me is the biggest place that's gonna move the wheel here.
Yeah, and that's something that a human would not be able to do, right? It's just being able to figure out which features are actually having the most impact. Well, I mean, theoretically, I guess you could, but that is a perfect application for an artificial intelligence system to do, is figure out which features are actually impacting it. I was listening to a podcast this morning. They were saying that they had trained the self-driving car, and I forget which company it was, but it was some artificial intelligence company that was doing essentially automated driving. And what they found was when there was a certain hue to the sky, the car would turn right for some reason. And after a lot of analysis and trying to scratch in their heads, trying to figure out basically what's going on, they realized when they had actually trained this car, they had trained it in Nevada, and the days that they had trained it, the sky had that color. And as it was driving around the track, it was every time it was making right turns, it basically thought it needed to make right turns based on the color of the sky. And it was one of these things where it was like, maybe they had too much data. Maybe it was too high fidelity. Maybe they had too many features going into this model that they were doing, and it kind of shot themselves in the foot. And it took them a lot of time to figure this out, and I'm sure they applied some of these techniques that you're talking about to try and narrow down exactly why this is doing it, because when a car's driving like this, they're probably taking thousands of inputs at any one particular time. And I just found it really interesting. I mean, I guess a lot of it comes down to feeding the right data into building the model.
Well, and you may not know the right data. So the way I was taught these methods by Dr. Haller was once you had a model that passed the statistical requirements to be valid. So, you'd done your internal validation, perhaps you'd even done some external validation. You had, if it's a continuous dependent variable, you look at your residuals, your errors, and make sure they're normally distributed. They're constant with respect to the dependent variable.
Mm-hmm.
They're constant with respect to the independent variables. And most importantly, in my mind, they're constant with respect to time. And so once you've satisfied those requirements, then I learned to, and of course I'm working with a linear regression, so I have an equation. So I can use that equation to hold, if I've got 10 features that are statistically significant, I can hold 9 of them constant at their averages and draw a graph to show you what happens when we vary that 10th one over the range that it varied in the data.
Mm-hmm.
And then you would prepare these 10 graphs and sit back down with your subject matter experts and say, this is what the math is telling us is going on here. When X1 increases, X, the dependent variable goes through an optimum at some point.
Mm-hmm.
Does that make practical sense? Can you explain this in terms of maybe the science, thermodynamics, the heat transfer, whatever it is, so that you don't get the color of the sky trying to direct which way the car's turning, because that would not pass a sanity check. Again, when we learned to do this, the tools were so clumsy and low power that even if you had the data, you couldn't afford to put hundreds of features into a model.
Right.
So you kind of did, for those people that are familiar with Six Sigma, as part of doing the causal analysis, you do a fishbone diagram, a brainstorming, where you try to characterize all the different types of influences that could affect the dependent variable. And from that, now sometimes you have a problem, like, again, if the toilet's leaking and you could put some type of an automation on the meter head to read the flow, there's a limited number of things that can cause that.
Mm-hmm.
But other times we'd have situations where there wasn't an obvious cause, and that's why this may be multifactorial, or the real tricky one is when the factors interact with one another, where the coefficient of one feature is dependent on the level of some other feature. Example I use, like in real estate, is they say it's location, location, location. So if you build a model to predict real estate prices, you will get a dollar per livable square foot coefficient,
right,
amongst other things. If you pick up a given house, let's say in my neighborhood, and you move it to Edina, which is a more expensive neighborhood, what's going to happen to the price of that house?
right.
And mathematically, what's going on is that the coefficient for square footage is changing. So the coefficient of square footage is a function of location. That's an interaction where the effect of one variable is modified by the level of some other variable. And interactions are hard to tease out by gut feel, even if you're the subject matter expert. But you learn, when you're brainstorming, you learn to listen to the subject matter experts. So when they tell you that, well, you know what, the cost of, for instance, to build a house on dollars per square foot is a function on what part of the country you're in.
Oh,
and the minute they say that one thing depends on something else, then that's an interaction. And you have to go fishing for that. Now, if you're using a linear methodology, you have to actually build that interacting term. If you're using something like a random forest model, any of those decision tree models, the second and third level branches of those trees are essentially interactions. They tell you that, well, when the variable A is at this level and variable B is at this level, here's what happens. And so those things, they come pouring out, and this is part of the place where the power comes from in those decision tree methods, is that they very easily can pick up on the interactions.
Yeah.
But I always like to go back to the causal system scientific principles. And at the end of the day, and this is one of the big problems I have with black box methods, is that it's hard to know what your model is actually doing. Like the example you gave, it took a lot of work, I'll bet, for them to figure out it was the hue of the sky that was causing that problem.
Yeah. And what I was thinking about when you said the black box thing is another big sort of thing that I've been seeing in the news that's been talking about is just the bias of some of these models, right? And you're feeding it so much data that then when people come and say this model's biased in a certain way, if you don't know what's really going on inside of it, inside of the neural net, because it's just so complex, it's hard then to justify or fight that or validate it or invalidate it if you don't understand what's really happening inside. And I guess that's what people are talking about a lot these days is these black box models are really cool, but they are biased. And how do you prove if they are, or how do you prove if they aren't, if you don't even know what's going on inside?
Correct.
Yeah.
There's a great book I read a number of years ago called Weapons of Math Destruction. That's MATH, destruction. And the book was full, of excellent book, but it was full of examples of how data science has kind of gone wrong because they perhaps didn't understand what was going on under the hood of the black box, or in some cases I've read about, the bias is actually built into the data.
Mm,
So the model has no choice but to be biased in its results because it was fed data that had the implicit bias built into it.
sure.
This is not an area that I consider myself having any expertise whatsoever, but I think particularly in light of what's going on today, it would be important to try to understand and root bias out of your models. And I know that we've got people at Optum that are working on that very thing.
Yeah, I'll be sure to put links to that book in the summary and description of this podcast. And since we talked, I actually have downloaded that on Audible, so they actually have an audio version of it. So I haven't started to listen to it, but I'm super excited to. So thanks for suggesting that. The other thing that I was thinking about is you had mentioned about not deleting outliers without trying to learn where they come from. Do you have an example like of that or use case about that?
Well, I tell you, the way I was trained as a chemical engineer when we did laboratory experiments and we would analyze the data, if we found we had an outlier data, and there's tools and statistics that you can use to try to determine, if you take the average and the standard deviation, if a given data point is more than 3 standard deviations away from the average, you might be suspicious about that value being an outlier. But we were taught as engineers to delete the outliers and then go back and rerun the analysis. And the first time I met Dr. Haller and I told him about that, he's like, they didn't ask you to go investigate it?
Sure.
Because, your systems, your process, your data collection, your technology produced that value. And if you think that value is bogus or has got some other problem, you need to go find out. Could it be the measurement? Like I had an example when I did some work with Chevron Chemical back in the 1990s, where they had a lab technician who turned his back on a wet chemistry titration, which is kind of the first rule of doing a titration. For any of those of you who have taken chemistry, you've had an Erlenmeyer flask with some liquid in it and with a magnetic stir, and you're dropping some titrant into that, waiting for a color change. And you can't turn your back on this thing because one drop, nothing. You'll see a little splash of color. The next drop, the whole thing will change. And this guy was multitasking. Now he's multitasking because they cut the staff and they had extra work to do. And that's I always brings to mind Dr. Deming, who said, you can hire a monkey to cut costs because it takes no particular genius to pull costs out of the system. Just get rid of the people, right? But to remove waste, that type of thing, bad defective product rework, delays, that kind of thing, to work those out of the system, that's how you really go about reducing costs. But every time this guy walked away from his titration, and if he missed it, sometimes he got back in time, and other times he'd turn around and there it had turned pink. And instead of rerunning the test, he just recorded the value and sent it out to operations. And now you've got a bogus high number that the operator gets in his hand and says, oh, my concentration of the fertilizer they're producing was too high. I'm going to change the process. And now you've just turned good product into bad product. And that's the result of having bad data. And that outlier, when we ran a test in the lab where we did blind replicate samples, and we found out that every time this one person, it wasn't every time they were involved in a pair, but every time there was an outlier, this one person named Gene was involved in the pair. And it turned out he was the supervisor who felt the most pressure to get the work done because his staff had been cut.
Yeah, sure.
So, and there's more to that story, but outliers are a golden opportunity to learn, which kind of gets to my next point is we need to learn how to look at the errors in our models as opportunities to learn. And so I'll go back to that meetup I mentioned where we were predicting the sales for the 50 fast food restaurants. It turned out they were Wendy's restaurants in the South and the Southeast. And what we did was you'd predict, we had 3 years worth of weekly, I think it was weekly data. And we would plot the errors, so the model errors. So over the 3 years, 52 weeks a year of data you had for this one store, you've got these errors. And the average error by default is 0. By definition, your average error for your model is 0. But when you plot these errors over time on a control chart, and you put reference lines at plus or minus 1, 2, and 3 standard errors, you find out that there's times where the model doesn't work on average. What I'm remembering was we stacked these charts up. So you might have had 20, 2013, 2014, and 2015 data on top of one another.
Yep.
And every October, like around the second weekend in October, you would have these shifts where the model was under predicting. And so what our analyst
Yeah.
did a Google search, figured out what happens in this small town in Alabama in October. And you know what it was?
I don't recall.
It was college homecoming.
Mm.
Right? And they had their homecoming weekend, and lots of people showed up, and Wendy's had a ball, right? Now, so that's not like we're taking our friends out for our, the alumni are going out for an expensive meal.
Right.
Turned out they were going out to Wendy's, but you learn. So I call that going to school on the residuals. You knew the model was having trouble. It just happened to be roughly the same weekend in October, all 3 years. And then she did the work and found out what that was. And so we built a homecoming feature. And then we could actually go back to this Wendy's restaurant and say, here's what homecoming's worth to you.
Right.
So for instance, in COVID, now with COVID, if they canceled homecoming, we could tell you, well, here's the kind of hit you're going to take in your revenue based on that. So that's what I mean by going to school on the residuals, is you have to study those errors and you plot them versus time. You plot them against the X's and you see if you can learn something that basically enhances your feature engineering.
Nice. Yeah, absolutely. One of the things we had talked about was then improving your model over time, right? I think a lot of people just build a model and they just continue to use it forever without actually enhancing it. Is that something you've seen?
Yes, yeah, it's rampant actually, and I would I'm kind of a troublemaker, so I knew I could get under on their nerves a little bit if I would state at one of these meetup groups or at a mini analytics conference that I'm not a fan of internal validation because my way of thinking, if you take a data set, your analytic data set, and you randomly sample it and split it into 70% train and 30% test, that it's a random sample. So really those two data sets should have the same information in them.
Right.
And now if you're using some of these high powered black box techniques, absolutely you have to do internal validation because you can build a model that fits that 70% very well, but not the 30%. So you're kind of obligated to do that. But to me, the real test is when you built the model and you put it into production, you need to monitor those residuals going forward to see how the model works on data it's never seen before. And again, I think of the concept of stability, that the errors in the model should be small, but they should be consistent. And so we typically run, in my work I do now with Optum, we run control charts. If we have weekly data, and every week we plot the model error on this control chart, and we run it out over time, and we look to see if the errors randomly bounce around zero. And if there's some bias, if at some point there's a shift that suggests either there's a new factor that's influencing your outcome, or perhaps one of your coefficients changed. And sometimes you're actually trying to change the coefficients. If you're trying to get more people, for instance, to accept an offer you have as a business, you might actually want to break your model. Like when I worked with the Art Institute of Chicago, we built models to predict the museum attendance. And long after I'd quit working with them, though, they had this great system for monitoring the models, and they had a bunch of different flavors. They had attendance for members, attendance for just the paid public, attendance for the local Chicago area, attendance for tourists,
Sure.
people coming from outside the state, outside the country. And when they were voted the #1 museum in the world by TripAdvisor members, their foreign attendance model broke 3 weeks later.
Sure.
Think about that. So imagine you're sitting in Europe, you're a TripAdvisor member, you see the latest rankings and say, wow, I didn't even know the Art Institute of Chicago was such a prestigious. You'd have to book a trip. You're not going to go tomorrow, right? You're going to go in 3 weeks.
Right.
And so,
Sure.
so they actually saw that their model broke, but the only reason they knew that is if the model's explaining 90% of the variance in the dependent variable, then when you're running these control charts, the noise you're looking at isn't 100% of variation in attendance. It's only 10% of the variation in attendance. And so you monitor those residuals, and then when you get what the control chart people would call a rule violation, a non-random event, a shift away from zero, your errors are no longer averaging zero. That's an opportunity to learn something. But in this case, they had this effect, and then after a number of months, that effect kind of died off again.
Yeah, sure.
But they said, you know what? We never saw a bump in the local attendance. So they ran a marketing campaign letting people in the greater Chicagoland know that the Art Institute of Chicago was number one according to TripAdvisor, and then their local attendance model broke.
Oh, interesting.
So
Like leverage that.
yes, they were smart enough to know how to leverage that. It's just a brilliant application. And by the way, it's one person doing all that work. That's one of the unicorns I know. Um, he builds the models. He knows how to do the coding. He's the database administrator essentially for their membership systems. He built the interface. He tied in all the weather data he had to go get, and the number one predictor of tourist attendance is hotel bookings. And so they get information from the Bureau of Tourism, and he built all of these systems to monitor that stuff. I actually had him present to a team I was working with at United Healthgroup, and they were like,
Nice.
how many people in your group? And he said, you're looking at them, just me. So small and
Uh,
mighty, power of a
yeah, sure.
unicorn. So it's if you have aspirations to work in the field of data science, Dan Atkins, who was the one of the co-founders of Mini Analytics, said that go back to that Venn diagram, and you should be expert in one of those circles, but you should be very comfortable moving. I think he actually referred to them as neighborhoods. You should be comfortable
Right.
negotiating your way around these other neighborhoods. If you're not the unicorn, at least you know how to go talk to the subject matter experts or the data wranglers, et cetera, so that you can accomplish an effective solution.
Yeah, yeah, that's awesome. Well, yeah, I mean, this got me thinking about just making sure you're not overfitting, right? I mean, is that what you're kind of doing when you're going back and running this and making sure that you are continuing to see the outliers like you expect, and it's not the model isn't really just predicting the data that you already have, and it's just fits so tightly to it.
Well, there's for anyone who's done any work with the more powerful tools like the decision tree models, they know they're taught to internally validate, to split the data into training and test, and to make sure that they're fitting the test data when they're not really training on the test data. The way that I learned this was really through two things. One was this sanity check, because if you
Mm,
overfit and you're graphing the effects, you will end up graphing effects that don't make any sense to the subject matter experts. And then one of two things can happen. Either the subject matter experts get educated because it turned out they didn't understand the causal system as well as they thought, or sometimes you find some problem in your data or some perhaps intercorrelation that created this nonsensical effect. So that's one way to learn about overfitting. And the other way I learned it is oftentimes in manufacturing, you're trying to predict something that is the result of a measurement. And as part of, in the world of Six Sigma again, there's a thing you do called measurement system analysis, where you essentially validate that your measurements are accurate, precise,
hmm
and stable. And again, stable means the accuracy and the precision is consistent over time. And sometimes you find that because of measurement problems, you get outliers. And so you can't predict outliers. Your
Yeah.
your your analytic data set probably doesn't have any features that speak to outliers. And so if those are coming from your measurement, and hopefully you have a method that you can remove those outliers. That's another way you can look at the residuals and see if your residuals, for instance, aren't normally distributed. Maybe they're bimodal. That might suggest that you've got potentially a measurement problem, or maybe you need some feature engineering to pick up that mode of residuals.
Yeah, yeah, yeah. Great, great suggestions and tips.
Or let me just, I say one other thing is that when you do a measurement system analysis, you get a standard deviation that's associated with that measurement. It's basically how much noise is in the measurement. And so when you're building a model predicting that measurement, you don't ever want your model to have less noise than the measurement does. So the way that you can check the standard error in your model to make sure it doesn't go below the measurement error. And that
Okay.
was another way that you could try to protect yourself from overfit. But I think the Cadillac solution again is to do some type of parsing of your data, random sampling into training and test.
Sure. That's a good place to start. That's sort of standard practice. Well, so I'm curious, what is a day in the life of your current role where you're at UHG?
I'm in now what's called Optum. So that's where one of your first speaker in your first podcast also came out of Optum.
Yeah.
And we're in the Optum Health Calls. And so he talked about how we have care delivery, and our organization basically does annual home health screenings for Medicare members. That's kind of in general, that's what we do. And it's a pretty high volume operation. We have practitioners throughout the country that we then, solicit members who are covered by our insurance or our customers' insurance. And we, if they agree, we can send a practitioner out to their home and basically conduct a pretty thorough home health screening. And for people that don't have transportation or aren't very highly mobile or don't have a primary care physician, we kind of can bring that technology to them. A big part of what we have to do is try to match supply and demand. And so the demand is coming from the members requiring a house call, and the supply is our practitioners. And we have to try to marry those things so that we can be as efficient as possible to try to keep the health system costs down for everybody. And so a lot of my work is involved in predicting demand and developing models to predict demand, but also developing models for key performance metrics like our contact rates and acceptance rates, et cetera, so that we again can monitor performance, but we can quiet down the noise in the data because we identify the causal system.
Neat.
So we know that some of our metrics, our performance gets worse as the year goes on, and we can adjust for those things so that we're not like feeling really good earlier in the year and then punishing ourselves later in the year, when in fact it's variation that comes from the causal system.
Gotcha.
So I'm a one-man shop, but I have a small data science team that I provide work direction to, and they're much more skilled in coding and some of the advanced methods. We make a good marriage. I think we're a unicorn.
Nice. All together, right?
Within our group. We're all together make a unicorn, yeah.
Excellent. That's cool. And so, like, how does somebody look to get into this field, do you think? I mean, you've got decades and decades of experience, and you shared a little bit about the wide range of fields you've been able to sort of take your analytic knowledge and scientific methods and sort of build that into. Are there any classes you would advise on? I don't know if you were part of the mini MUDAC stuff that Dan Atkins, and the mini analytics team ran. Are those types of fun competitions to do? What might you suggest?
I absolutely. In fact, if people are listening to this podcast, then that's a good sign that you're doing one of the things that's correct to be in this field. Again, I think more broadly about data science education, and that I think you should learn some of the concepts of Six Sigma, so some basic methodologies around process improvement. I think would be helpful to make you more effective as a data scientist. Definitely getting involved in meetup groups. And if you're in college, these MUDAC and mini MUDAC things are fabulous opportunities to learn. And you really have to, even like for me, is once I figured out how the power of building models, I have since 1989, I've never done a real estate transaction without a model to predict the prices, whether I was buying or whether I was selling. And what I've learned, and that was, well, a couple of things about that. It's I could probably add up maybe $60,000 to $70,000 I'd either made as profit or saved as cost because I had a better idea of the pricing than the real estate agents did. And my motivation was to maximize, my net worth. Their motivation oftentimes is, they need to get the sale, right?
Right.
They have to try to get that commission because they need to get on to the next one. And so I never let them set the price anymore. I always do that myself. I bought a motorhome one year and got a great deal because I had a model, and I flew to California, inspected this thing, paid for it, and drove it home. One would pop up. They didn't sell that often. I was looking for this thing used, and when they did, I'd immediately put all the particulars in my model to see if the price was reasonable. And if they were asking too much, then I wouldn't pursue it. But if it looked like I could get a good deal, then that's eventually what I did.
Yeah.
And that's a great way to practice. And, I've always had access to software that I could leverage to do this. But now with the open source tools, which is the thing that I think if you want to get into this field, you've got to learn open source and learn how to code. Then you can go online and download, RStudio yourself or do some work in Python and import the packages you need and find applications in your personal life. When Dr. Deming said, back in 1987, this will change your life.
Yeah.
Again, I thought he was nuts. But I am a tried and true data geek, and it turned out I'd found my calling in life, and that chemical engineering was not really ever going to be my calling. It was a great education and taught me how to problem solve and taught me about the value of science. But when I learned about how to handle data, that's what really opened up doors for me. I actually visited. There's a woman who writes an article that's really good in the St. Paul paper, Amy Lindgren, and it's in the business section. And I haven't taken the St. Paul paper in a while, but I did.
Yeah.
They're trying to get me to subscribe, so they dropped a free one on, and I saw she's still in the paper, but she runs a consultancy for job search, helping people land jobs. And so I actually engaged with her, did some coaching, took some of her classes back in 2008.
Yeah.
Basically, the economy tanked, and my work as a consultant dried up in about a week, 2 weeks maybe. I just had cancellation one after the other, and there I'm looking. So
yeah, sure.
So I thought I'm going to have to find a job, like a real job where you actually go to work every day. And so I had no idea how to do that. And so I engaged her, and what I learned was everything you need to do to get a job, the networking, the engaging in things like meetup groups, the volunteering with nonprofits, anything you do to be helpful, make a connection, learn things, those are the exact same things you need to do to freelance as you need to do to find a job. And once I learned that, I thought, well, I'm just going to apply what she learned into freelancing. And eventually I got my work back, and I didn't end up taking a job until 2015. So I lasted another 7 years.
Great advice. I got to bring you along when I buy my next car or invest in the stock market. I don't know if you dabble in those things as well, but those are good things to analyze, right? Like you can spend forever and try and analyze when to buy a stock.
Yeah, and that I've never actually tried that, so I have not, because I pretty much all of my investments are in index funds. Very, very low cost, no turnover. I'm not paying high fees because I'm of the mind that Deming had a saying that an unstable process. So this is the process that's under the influence of what he called special cause variation,
sure.
non-random events. There's books out about, like if you Google Black Swan event, there's great books about what the Black Swan is. And COVID-19, the whole coronavirus thing is a great example.
Right.
6 months ago, well, maybe not 6, maybe 8 months ago, nobody would have predicted what's going on now, that you could get gas. I heard people saying they got gas for under $1 a gallon at the bottom of the petroleum prices. And there's nobody who could have forecasted that. So an unstable process, there's no rational basis to predict the future. And if you could predict the stock market, there'd be smart people doing it already. So nobody can actually beat the market consistently without cheating. So that's why I'm heavily invested in index funds.
It totally makes sense. I mean, it's such an emotional buy. You know what I mean? That's the thing. It's that sometimes it just defies logic. And when you were talking about, not even knowing what's coming up, Nate Silver has a book that I might have mentioned before called The Signal and the Noise, and he talks about sort of the unknown unknowns. Right. That's what you're talking about is when you say the black swan, right? It's just these completely unforeseen. It wasn't even a part of your model, and you never even thought that this would ever occur. And once those things happen, then you're getting into territory where, you don't have any historical data
to predict.
To basically predict on it. Well, how do people reach out to you? I think you're on LinkedIn. Is that probably the best way?
Yes, that would be. Although I'm the sole parent for two. I'm an old guy who's got very young kids, and so particularly when they came home and had to be homeschooled, and I'm a telecommuter, and that just blew up my calendar. So my time is very limited. But if you've got some question you think I might answer, feel free to contact me on LinkedIn, and be patient waiting for a response.
Well, cool, Kevin. Well, thank you for, all that you've done, in your career, but also be with a lot of these organizations, Star 82 and nonprofits. And I've seen you just teach classes, being a mentor to all these data scientists and people that are coming up. So I definitely appreciate you doing that, and look forward to continuing to do that in the future. You have a lot of great knowledge and information to share. So I appreciate you being on the podcast again.
Thank you. It was a pleasure.
All right, take care.
You've listened to another episode of the Conversations on Applied AI podcast. We hope you are eager to learn more about applying artificial intelligence and deep learning within your organization. You can visit us at appliedai.mn to keep up to date on our events and connect with our amazing community. Please don't hesitate to reach out to Justin at appliedai.mn if you are interested in participating in a future episode. Thank you for listening.